You know, for over a century, Einstein's general relativity has been our map of the cosmos. But what if that map is missing a crucial detail? Today, we're diving into a pretty radical new idea called omega-GR. It's a theory that suggests the very fabric of spacetime isn't just some passive backdrop for reality, but an active participant with one single all-important job to do.
Okay, so pretty much all of modern physics kicks off right here, with Einstein's legendary energy-momentum relation. For 100 years, we've treated this as a basic fact of the universe. It's just how things are. It's the bedrock math that ties together energy, momentum, and mass for anything, anywhere. It's been an unshakable pillar of physics.
And this is where omega-GR throws a massive curveball. It asks a really profound question. What if this equation isn't just a description of reality? What if it's a strict law that the universe has to actively enforce, moment by moment, at every single point in space?
And that one shift in thinking, right there, is the entire foundation of omega-GR. It takes a passive mathematical fact and makes it the main engine of the cosmos. The equation stops being a result of physics and starts being the cause of it.
So the theory takes that famous equation and gives it a new job title, the omega constraint. And the core principle is that this value, omega, must equal zero, always, everywhere. It's not just a nice outcome of the laws of physics. In this theory, it is the law. The universe's prime directive, if you will, is to make sure this one condition is always met.
Right, but that immediately brings up another question. If the universe has to enforce this rule, how in the world does it do it? What's the enforcement mechanism? Who's the cosmic cop on the beat?
The theory's answer is something totally new. A universe-spanning field called chi. You can think of the chi field as the universe's enforcer. It's everywhere all at once, and its only job is to constantly adjust the fabric of reality itself to make sure that omega constraint is never, ever broken.
Now this is a huge paradigm shift. I mean, think about it. In standard physics, we think of space-time as a stage. Sure, it can get curved by mass and energy, but at the end of the day, it's a passive backdrop. In omega-GR, spacetime gets off the bench and becomes an active player. The chi field makes it this dynamic, responsive thing that's constantly changing based on the matter and energy inside it.
So what this means for, say, a planet or a photon moving through space is that they're no longer just following the curves made by mass. They're following what the theory calls an effective metric. This is the actual geometry they feel, a mix of standard gravity plus the direct influence of the chi field's constant adjustments.
And this idea of a responsive, state-dependent geometry, well, this is where things get truly mind-bending. This is where the theory leads to its most controversial consequence, because it changes the fundamental nature of gravity itself.
We've all heard that a kilogram of feathers falls just as fast as a kilogram of lead. Well, general relativity says gravity is totally democratic. It pulls on everything, matter, energy, light, in exactly the same way. It plays no favorites.
Omega-G looks at that core principle and says, maybe not. Because the chi field's job is to enforce a rule, it could interact with particles differently depending on what they are. This opens the door for gravity to be, well, not so universal after all.
The theory pulls this off with a really simple but powerful little mathematical switch. It's called sigma. It just assigns a value, +1 for matter and -1 for antimatter. It literally builds the difference between them right into the main constraint.
So that enforcer field, chi, actually interacts with this little sigma tag. And the result is profound. The gravitational curvature that matter feels could be different from the curvature antimatter feels. Yes, you heard that right. This leads to a startling prediction. Matter and antimatter might not fall in the exact same way.
A wild idea, right? But physics isn't just philosophy. A good theory has to make predictions we can actually go out and test. So where in the universe would we even look for the fingerprints of this chi field?
We look to the most extreme places we know of, black holes. In standard physics, there's the famous no-hair theorem, which basically says black holes are incredibly simple, bald even. You only need to know their mass, charge, and spin. Any other detail gets wiped clean. But in omega-GR, the chi fields can leave an imprint, a kind of constraint memory, and this gives the black hole new measurable properties, a form of gravitational hair.
And this hair would make for a very different beast. Instead of being perfectly symmetrical, a black hole's gravity could be lopsided or anisotropic because of that lingering chi field. The natural paths that things follow around it would actually depend on whether they're matter or antimatter. Even the point of no return, the event horizon, and the way the black hole bends light could be distorted in unique and observable ways.
So what are astronomers actually looking for? These are the smoking guns. They're looking for asymmetric, lopsided shadows around black holes. They're looking for strange hiccups in the gravitational waves from merging black holes that might be carrying this constraint memory. And here's the big one. High-precision experiments right here on Earth that might find that different kinds of matter fall at infinitesimally different rates. We could even see a new kind of Hawking radiation, where a black hole evaporates by spitting out more matter than antimatter.
But, finding a weird signal from space is only half the battle. For any new theory of gravity to really work, it has to survive the ultimate trial by fire, the wild, unpredictable world of quantum mechanics.
And this is where the theory faces its greatest challenge. It's called the anomaly risk. See, down at the quantum scale, reality is just a fizzing sea of random fluctuations. The danger is that one of these quantum jitters could spontaneously break the Ohm constraint. And if that happens even once, the entire mathematical structure of the theory just falls apart. Game over.
So, to stop this from happening, the theory has to perform this incredibly delicate balancing act. It involves introducing other theoretical fields, sometimes called ghosts, whose only purpose is to cancel out all that dangerous quantum noise. It's a process of tuning the theory's parameters with absolute precision, making sure that the quantum jitters from spacetime itself and the jitters from matter perfectly cancel each other out, keeping that all-important constraint safe and sound.
This intense focus on just maintaining the rule, it really reveals the deep philosophical heart of omega GR, and the authors sum it up perfectly. They say that in this view of the universe, the most fundamental thing isn't space-time, and it isn't fields. The primary object, the thing that matters most, is the consistency of the constraint itself. Everything else we see is just a side effect of the universe's tireless effort to obey that one rule.
Which leaves us with a final, massive question. Are the laws of physics just these static, unchanging rules written in stone? Or is the universe a much more dynamic place, constantly working and adjusting to maintain its own consistency through a process of continuous self-correction? Omega GR boldly suggests it's the latter. And if it's right, well, that changes just about everything we thought we knew about gravity.